Hey, let's talk about converse of the multiplication rule. Again, it's with compound probability. We've got more than one event happening, and in this situation, it's all about rolling dice and the sort of outcomes you get from either adding the dice or multiplying the dice, but how often does something happen? Here's my token dice or die element. The result of 3 on the first number cube. Let me start at the beginning. You've learned that if two events A and B are independent, then the probability of the events occurring is probability of A times probability of B. So highlight that in. That's when they're independent. But the converse is also true. And in the converse, we say, let's just calculate the probabilities separately, multiply them, and check if it's the same result as if we had determined the intersection. And if that is a true equation, then we can conclude that the results are independent. The events are independent. See the order there? Like, we're first of all going, independent means the formula, but the converse means the formula tells us independent. And so we want to be able to go interchangeably with that multiplication rule for the independence of events. Let's consider that for 1a. Use the converse of the multiplication rule and the sample space you created in the previous activity to determine whether the events are independent. The results of a 3 on the first number cube and the results of a 3 on the second number cube. So here's one thing that we know. The results of the first die, so that's one of those, and when you roll it, you rolled off the screen, get a 3. I got a 3. So the results of that one do not interact with the results of what I roll next. And I didn't roll a 3 that time. So therefore, this is an independent situation. Mathematically speaking, if we do A times B, so that's the probability of a 3 first, 1 out of 6, times the probability of a B second, another 1 out of 6. That's 1 out of 36 when you multiply them. But if I look at this table and I think about how this is first and this is second, then rolling a 3 first and rolling a 3 second is this cell. And it only happens once out of the entire group of 36. So 1 out of 36 is the outcome just by counting from the table. Maybe it's worth a highlight. This is question 1a, so I'm going to highlight 1a there. Then I'm going to go back to the table. I'm going to highlight. That's the only cell that happens to be a 3 first and a 3 second, and it's 1 out of 36 total outcomes. That's independent. That's what independent means. This half of the equation equals this half of the equation, and there's the mathematics that justifies it. Next question. The results of 2 3s and a sum of 6. So what we need to do is figure out the results of rolling 2 3s. Then we need to figure out the results of rolling a sum of 6. And then consider what's the combination of all of that together. Okay? Because if we get an equation that's a true statement, then we can say the events are independent. If we get a non-true equation, then they are not independent. So let's consider this one. First of all, rolling 2 3s is a 1 out of 36 chance because it's the only one that's highlighted in the option. Rolling 2 3s. Yellow. Now, rolling a sum of 6, we can take a look at the probability table and realize rolling a sum of 6 5 times out of 36, that happens. So there are 5 different outcomes from the sample space that produce a sum of 6. There, 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 and there. That's a 1 and a 5, a 2 and a 4, a 3 and a 3, a 4 and a 2, and a 5 and a 1. Now notice, I said 1 and 5 twice because one die could be 5 and then the other could be 5 when you look at them separately. So if there are 5 outcomes, there is 5 out of 36 ways to roll that. Hey Siri, what's 36 times 36?
36 times 36 is 1,296.
Okay, there's 1,296 different combinations of 36 and 36 dice. So if we do 2 things together. So if we roll 2 3s and a sum of 6, that only happens once. That only happens there. That's the sum of 6. That's also 2 3s. The and is the key word. And, so it has to be both. So 2 3s and a sum of 6 is once out of those. These are not equal fractions. I hope you know that that's true. These are not equal fractions. But if you needed to, you could divide. Hey Siri, what's 5 divided by 1,296?
5 divided by 1,286 is approximately 0.003888.
96. It's supposed to be 96. Siri's not wrong though. Hey Siri, what's 1 divided by 36?
It's approximately 0.02777.
Not the same. Not the same. The events are not independent. You could say ergo, that means they're dependent. That's probably fine. But I'm going to leave it here as is independent or is not independent and allow the double negative to happen. A result of 6 on the first one, highlight time, and a sum less than 7. So a result of 6, there are 5 different ways to get a sum of, no wait, a result of, that means 6 is the first die throw. So 6 is the first die throw is this entire row. There are 6 of them. And then getting a sum less than 7. So a sum less than 7 are these 15 outcomes out of 36. Hey Siri, what's 1 over 6 times 15 over 36?
1 over 6 times 15 over 36 is approximately 0.06944.
0.69, oh, 06. There we go. Okay, so then if we want to talk about getting all of that together, getting a 6 first, and then getting a sum less than 7, a sum less than 7 means you can't have a 6 be rolled at all. This one is 0 out of 36. That one will not happen. Do you see that? A 6 on your first roll and getting a sum that is definitely less than 7 with your second roll added to the 6. Lowest number of the second roll could be is a 1. So 6 plus 1 is 7. That's out. So there's 0 chance you're going to get this one, and therefore these events are not independent. It's also kind of a stupid comparison. Like sometimes we have that, you're like, okay, yeah, 0. Notice when the 0 probability happens. Some questions before we answer the last one. What is the purpose of the converse in the multiplication rule? You know, the directionality is what that says. What you are assuming to then establish what you're trying to conclude. Another question. Once you determine the probability of A times the probability of B equals 1 out of 36, how do you verify whether or not probability of A and B have the same result? You look at your sample space. You actually list all 36 outcomes and you pick the one or more than one if it is that actually has that. So it's good to have all of that like up here, like you're thinking about your different arrangements, but you still want to be able to like identify it for yourself. This is that outcome. Okay, last question. A result on any number on the first number and a sum less than 7. Well, the nice thing about this one, any number on the first number, there are 6 different ways you could roll the die and just get a number. That's a number. I got a 5. Okay, reset. What's the probability of getting any number? Guaranteed. I got a 1. Guaranteed. There are 6 different arrangements for that die. Times a sum less than 7. We already know that a sum less than 7, there are 15 of them. That's the nice thing with these questions. So we don't have to keep hunting for further structures or probabilities, but they're there. You should have that skill in mind. 6 over 6, 1. So this is really 15 over 36. Now we need to check whether or not that equals the probability of any number and a sum less than 7. So I have any number out of any number possible, and there are 15 of them that are less than 7 when you add them up. So 15 out of Oh, out of 36, 15 out of 36, sums less than 7. These are equal. This means the events are independent. So when we talk about independence and dependence, it's all based upon the formula. We want to be able to check whether or not the probability of A times B is equal to the probability of A and B. The only way you know the and is you actually list them all and you count. Okay, we are going to move on to analyzing two-way tables in the next video. So thank you for watching this one, getting your notes captured. It's been a deep conversation, and there is a lot of deep stuff to talk about in topic 2. So thank you for sticking around and learning and doing your best. I'll see you in the next episode. Have a good one.